All right, chapter 8. This is going to be a very long video, right? And if you're paying attention to the syllabus, you should note that I spend 3 class periods on chapter 8 because it's a lot to take in. This really is sort of a kind of a pivotal moment in the class because it's sort of from this point that we really start to learn the first of the statistical tests, really sort of rooted in kind of how we use them to answer questions about research and psychology. So it's worth it to take a little bit more time here. So don't feel that you need to watch this video from beginning to end in one sitting, right? You can break it up over a period of 3 days. And I'll even give some areas where I suggest as good as time as any to sort of take a break, if you will. So, right. So we've been performing analyses so far where we've been interested in where a single score fits into a distribution. And the other day we started talking about how probable a sample of data is given some sort of population mean and standard deviation from which they came from. Right. So now we're going to get into the heart of what statistics is used for in science. We're going to start asking questions about how a sample compares to a population mean. Really asking whether or not is it different or not, right? And we're eventually going to transition to asking questions about whether 2 or more group means are significantly different than one another, right? That'll get more sort of complicated. But from here all the way until the end of the semester, we're going to be employing a tool that we call hypothesis testing. So it's a statistical method that uses sample data to evaluate a hypothesis about a population, right? It's an inferential procedure, right? It allows researchers to use sample data to make inferences about a population of interest. So, for example, maybe I hypothesize that college students spend 70 minutes a day or more on social networking websites. And so I can gather a sample of 300 students and I can compare their mean to my prediction, right? So I'm using my sample to make inferences about the behavior of a population. It's a logical process, right? It's an if-then process. If college students spend 70 minutes a day on social media sites, then if I test a random sample of college students, I'd expect to find that they also spend around 70 minutes a day or more on social media sites. So the crux of how this works is, we state some sort of hypotheses or predicted characteristics. We obtain a random sample from the population and run an experiment. And then we compare that sample data with a prediction. And there are 6 steps to hypotheses. If you're taking notes, get these into your notes. We're going to talk about each of these steps in detail. And I don't feel like I'm giving you anything away when I can tell you that I don't know, maybe not. You can expect on, say, the next exam, maybe or maybe not, to list and describe these steps. They're very important, right? Because these steps are something that we're going to be using for the remainder of the semester. Our statistical tests that we learn how to run may change, and some of the ways in which we do these 6 steps may change, right? Or they will change for sure. But these 6 steps is something that we will always continue to revisit as we learn additional statistical analyses, right? So as I explain the intricacies of hypothesis testing, I'm going to use several examples that we've talked about from previous lectures, right? Like our made-up baby crawling data, for example. And in this case, we're going to be doing a one-sample z-test, right? And it's basically what we learned how to do last time in chapter 7, right? The sample mean minus the population mean divided by the standard error of the mean, right? So it's a one-sample z-test. We're going to be calculating a single z-score for a sample of data, right? It could be babies, SAT scores, whatever. And we're going to be comparing it to a population mean. So the good news here is you should feel quite comfortable with the math at this point, because we've been doing z-tests themselves for a couple of weeks now, and you should feel after last lecture in the homework comfortable with doing a one sample z-test. So just sort of set the stage here, right? We perform a one sample z-test when we know the population mean and especially the population standard deviation, right? Really, the population standard deviation is critical. We cannot compute a one sample z-test if we don't know the population standard deviation. And the logic here is quite simple, right? If we collect a sample and we compare it to some sort of hypothesized population mean, and we ask, is our sample mean statistically different than the population mean? So the very first thing we need to do when engaging in hypothesis testing, I don't care if it's this class, when you take research methods, if you have a career as a scientist or a researcher, the first thing you have to do is explicitly state the null and the alternative hypotheses. And when we state the hypotheses, that means we're generating two separate opposing hypotheses, a null and an alternative. And the null hypothesis, and note, and I'll get into this, we use H subscript 0, right? The null hypothesis is that there's no effect or no change or no difference, right? It simply means that we don't expect there to be a difference between our sample mean and the population mean. The second of our predictions is what we call the alternative hypothesis. This is denoted by H subscript 1. And that's essentially saying, well, there's some sort of effect or change or difference between our sample mean and our population mean. We're going to sort of write some of these out in a bit as we go through a couple more slides. But we always state the null and the alternative in terms of population parameters, right? Even though we're talking about how a sample compares to a population. So it's just a fancy way of saying that we're going to be using Greek letters to talk about our sample, even though what we're really talking about is sample data. So a couple of things before we get into sort of the details of how you use statistic notation or mathematic notation to state a null and alternative hypothesis. How you state the hypothesis depends upon whether the test is a one or a two-tailed test, right? And that depends on the experimenter's predictions. So if something's a one-tailed test, it means that the experimenter predicts that their sample mean is going to either be greater than or less than the population mean. One of those two, right? That means the experimenter predicts that their sample mean is going to be either greater than or less than some sort of hypothetical population mean. Now, I find there's a bit of a strategy here. Remember, you've always got to state two hypotheses, the null and the alternative. And I think when you determine that a test should be a one-tailed test, I think it's a nice strategy to start with the alternative hypothesis first, state that, right? An easy way to sort of think about this is the alternative hypothesis represents the researcher's directional prediction, right? So it's what they would expect to find, right? It's what they would expect their results to be if their experiment worked. So let's just jump right into it here, right? Here's a scenario. And what we want to determine is, what type of test this is. So a researcher predicts that children, oops, I got a little typo again. This is why I actually do it like this, so I can fix things when I see little mistakes. All right. A researcher predicts that children will learn to crawl earlier than the population mean after taking his motor development vitamin. So there's a prediction here, right? And that prediction has a direction. So let's think about this, what this means. Learn to crawl earlier, right? That's the key. You should think about this as you're reading these scenarios and trying to figure this out. Learn to crawl earlier is the key here, right? Now think about that phrase. Does the researcher think that his sample mean will be less than or greater than the population mean? If he's saying that his prediction is the babies in his study will learn to crawl earlier. You could learn to crawl earlier than the population mean, right? He's making a prediction. If the population mean is 36, his prediction is that his babies are going to learn to crawl before that, right? I don't know, it could be 35 months, 33 months, 29 months. I don't know, right? We're not at the stage where we're talking about that. We're just asking, what is the direction of this prediction? And it seems to me to be a less than prediction, right? The researcher predicts that their sample mean, right? Their sample mean, which is the children that will learn to crawl, blah, 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 will be less than the population mean of 36. So if that's the case, we want to start by stating the alternative hypothesis first, because the little operator that we use here is going to reflect whatever direction we determine the alternative hypothesis to be in the scenario. So a couple of things that are very important here when you're writing things in statistical notation. So again, I've already got the prompt of the null started, but we're going to focus on the alternative here. H subscript 1 colon, right? That's exactly how you start off your alternative hypothesis. You need to do that every time. And remember, I told you we were going to talk about it, even though we're talking about a sample here, we're going to use population, Greek letters that are typically associated with population parameters to do so. So you're going to put a little mu sign after that H1 colon. And then you want to put in a subscript here, some sort of one or two words that best represents the dependent variable. So let's go back to our example here. If you recall from these data before, babies we were measuring the month at which babies learn how to crawl, right? So here I've described it as crawling age, but you could easily describe it as months, right? So all this is saying is the alternative hypothesis is that our sample mean, right, should be less than our population mean, which is 36, right? So again, we came to the conclusion that this prediction embedded in this description of this scenario suggested that the sample mean for the researcher should be less than the population mean. And your operator that comes after your mu in descriptive term of the dependent variable needs to reflect whatever that prediction is. So in other words, it would be less than. And that should always be followed with whatever the mean is of the population. In this case, here it is right here. The mean is 36, right? So our alternative hypothesis is that our sample mean should be less than our population mean of 36 months. And you could even actually say 36 months after this. It's fine. Okay. So, like I said, it's easier to start with the alternative hypothesis because, as you can see, the alternative hypothesis for a one-tailed test is embedded in the prediction, right? So all you have to do is figure out which direction that prediction is and then notate it accordingly. Once you've done that, stating the alternative hypothesis is very, very easy, right? So everything is going to be the same, except the operator is what's going to be different. So you're going to have this H subscript 0 colon. And so all of this, right, mean crawling age, that's going to be up here as well. And 36 months is also going to be up here. But what's going to change is the operator. And it's quite easy. The operator for the null hypothesis is the opposite of your alternative operator, right, with an equal than as well. Right? So let me just show you. So our null would be, and let me fix this because it'll drive me crazy. Our null would be that the mean crawling age for our sample should be greater than or equal to 36 months. And let's think about what these mean in just simple language. Even though this is a greater than or equal, what it really means still is that our sample crawling age should still be equal to our sample mean, right? I know we're using the greater than or equal, but it's just sort of a technicality. What it means in the real world is that we would expect no difference between our sample and the population, right? Under the assumption that the null is true. Whereas alternatively, we expect our sample mean to be less than our population mean. Okay? Don't worry if that was a little hard. We're going to do a couple more. Same example here is say a researcher predicts that children will learn to crawl later than the population mean of 36 months after taking his motor development vitamin. So what do we got here? A one-tailed or a two-tailed test? Hopefully your answer was two-tailed test, right? And what's the direction of the prediction here? Would we consider this, do we think that learning to crawl later than the population means that the sample mean should be less than or greater than the population mean. Hopefully you said greater than, right? Because to crawl later than 36 months insinuates, it doesn't insinuate, it explicitly states that we expect the sample mean to be more than 36 months, right? So we would expect this to be a greater than prediction for our alternative hypothesis and a less than or equal to for our null. And here it is, right? Here it is. Again, I would state the alternative hypothesis first. So H subscript 1 colon, mu crawling age should be greater than 36. So the crawling age for our sample should be greater than the population mean of 36 months. Whereas our null hypothesis should be that our mean crawling age for our sample should be less than or equal to 36 months. But again, remember in English, we're just saying, look, there should be no difference, or alternatively, our sample should be greater than 36 months. In a one-tailed test, the alternative hypothesis, and this is just an easy thing to sort of keep in your memory, it's always going to be either a less than or a greater than sign, right? In the alternative hypothesis for a one-tailed test, it can only be a greater than or less than sign. And the null is always going to be its opposite, plus the little equal bar that goes at the bottom, right? So you can almost rote memorize this if you're really having trouble wrapping your head around it. Let's think about a two-tailed test. This is a little bit easier. And a two-tailed test means the researcher doesn't have a directional prediction, right? So the researcher is essentially saying, the sample mean should be different than my hypothetical population mean. Maybe it's going to be greater, maybe it's going to be less, but for whatever reason, the researcher doesn't have an a priori, right, meaning before the experiment, an a priori reason for predicting whether their sample mean should be less than or greater than the population mean. They're just sort of saying, well, we expect there to be a difference. And here's an example, right, using our vitamins again of kind of what I'm talking about. So a researcher predicts that his vitamin will have an impact on the age the children in his sample will learn to crawl compared to the population. And so again, the key word here is impact. You're not seeing anything, the researcher predicts it's going to be less, or the researcher predicts it's going to be more. Impact is very general. So to have an impact, it means that it could improve crawling times, or maybe alternatively, the other side of the coin, it might worsen crawling times, right? A lot of times you might see it stated, a researcher was interested in whether or not there is a difference between the sample mean and the population mean. Again, there's no clear directional prediction. So if that's the case, then it's a two-tailed test. And now stating the null and the alternative for a two-tailed test becomes trivially simple. Everything that was true before, right, where you have your H subscript 0 in your colon and your H subscript 1 in your colon, and then you have mu, and then in the subscript you write some sort of one or two words that represent the dependent variable. Then there's going to be an operator, and then that's going to then be followed by some value for the sample mean. All right, so all that you did before is true. The only thing that changes now is the operators, right? And now the operator will be an equal and not equal sign, respectively, for the null and the alternative. So in this scenario, our null and our alternative hypothesis would look something like this, right? So the null would say that the mean crawling age for our sample should be equal to the population mean of 36 months, whereas alternatively, the mean crawling age for our sample should be not equal to the population mean of 36 months. So in other words, again, a crawling age could be less than 36, or it could be greater than 36. We don't have any sort of prediction ahead of time. So in a two-tailed test, the null is always an equal sign for the operator, right? Equal to the population mean, whereas the alternative is always the not equal sign to the population mean. Also important, not just in terms of stating the null and the alternative hypotheses, but also important if a test is one or two-tailed, impacts how we're going to select our decision criteria, which is what we're going to do in step 2. But we're still dealing with step 1 right now. So not only is whether you're determining whether a test is a one-tail or two-tail test in the scenario, determining whether that's important for stating the hypotheses, but it's also important when you select the decision criteria. Okay. Let's do a couple of practices here. So you're conducting a study investigating the effects of caffeine on memory. An analysis of the population data for the memory test shows a mean of 40, right? A population mean of 40 and a standard deviation of 5. You predict that caffeine will show a difference during testing. So first of all, determine whether or not this is a one or two tail test. And then I want you to take a stab at writing the null and the alternative hypotheses. So go ahead and give that a shot and pause the video. So hopefully you determined that it was a two-tailed test, right? Because note here, you predict that caffeine will show a difference during testing. You haven't made any clear directional prediction in this scenario, right? You haven't predicted that caffeine will improve memory. You haven't predicted that caffeine will impair memory. You've just simply stated, right, that you predict a difference during testing because of caffeine. So two-tail is the appropriate response. And then remember our rule of thumb here. If it's a two-tail, the null operator is going to be equal and the alternative is going to be not equal. So for the null hypothesis, H subscript 0 colon, then our little mu sign and memory, because that's what we're measuring here. I didn't give a whole lot of detail here, probably some sort of test scores or something, but test would be fine, memory would be fine. I'm not going to, as long as whatever descriptor term you use here does a pretty good job of close enough of representing the dependent variable in some way, you're not going to lose any points. So our mean memory scores for our sample should equal the population mean of 40. Whereas our alternative, H subscript 1 colon, the mean memory scores for our sample should not equal 40. Again, caffeine could make it worse. It could make it better. We're not making any prediction prior to running the experiment. Let's do another scenario here. I think I want to do 2 more. You're conducting a study investigating the effects of video games on aggression. An analysis of the population data on an aggression test shows mean scores of 75 and a standard deviation of 12. You predict that video games should lead to an increase in aggression. So again, determine whether or not this is a one or two tail, and then state the null and the alternative hypotheses. Pause the video and give it a shot. So hopefully you said it was a one tail, right? Because you predict that video games should lead to an increase in aggression, an increase in regression. So you predict that whatever our sample is going to be greater than this population mean of 75, right? So because there's a directional prediction, that means that we're running a one-tailed test. And again, when it's a directional prediction, I think a good strategy is to start off with the alternative hypothesis, because the alternative hypothesis should reflect exactly what's being stated in this example, right? So H subscript 1 mu aggression, right? Because that's what we're measuring, right? The mean aggression of our sample should be greater than, right? An increase compared to the mean. So greater than our mean, sample population mean, which is 75. Whereas our null, again, is just simply the opposite of our sign here with the equal to as well. So the aggression for our sample, the mean aggression for our sample should be less than or equal to our population mean of 75. Let's do one more, right? The population mean score on the RADS is 60. Come on, man. What's wrong with me today? 60. I don't know where I got 84. 84 would be an incredibly high score. Anyway, the population mean score on the RADS is a mean of 60 with a standard deviation of 14. And we said scores of 77 or higher indicates the risk of the development of depression in adolescence. You predict that your depression intervention should reduce RAD scores. So, again, my typos notwithstanding, is this a one or a two-tailed test? And then I want you to state the null and the alternative hypotheses as well. Give it a shot. Yeah, so this should hopefully be a one-tailed test. That's the answer you came up with, right? Because you predict that your depression intervention should reduce RAD scores, right? So you have no idea what it's going to be, right? It could be 59, it could be 54, who knows, right? But you're making the prediction that your intervention, right, should reduce RAD scores, right? So your alternatives should be H subscript 1 colon. And again, mu RADs, right? We're saying that the mean RAD score for our sample should be less than, right? Reduce less than this mean of 60. Whereas the null hypothesis should simply be H subscript 0 colon, right? Mu RADs, right? The mean of our mean RAD scores for our sample should be greater than or equal to the population score of 60, right? So again, this is just saying we don't expect a difference, right? That's the null. We don't expect a difference between our sample mean and the population mean, whereas this is saying we expect our sample mean to be less than 60. Okay. Again, don't worry if this is a little complicated still. We're going to have plenty of opportunity to do some examples. Sorry, I had to have some water there. Okay, that brings us to step number 2, determining the decision criteria. So what we need to do here is and this is going to involve using our unit normal table, right? So this is going to involve looking up probabilities and then finding corresponding z-scores associated with these probabilities. And we're going to use those z-scores. We're going to call those z-critical scores. And we're going to use those as cutoff scores, right? So that when we run our test statistic, right, we compute our test statistic in step 3. In step 4, we're going to compare the results of that test statistic with this criteria that we set in step 2. And that's going to allow us to answer whether or not our sample mean is significantly different than our population mean. So we need to select a probability as a cutoff for what we think would be an unlikely sample mean to get when we run our experiment under the assumption that the null hypothesis is true. And in psychology, that conventional cutoff, it's also something that we refer to as an alpha, but that conventional cutoff is 0.05. Sometimes you'll see, you might have read some papers where that cutoff is even lower, 0.01, 0.001. I'll talk a little bit later about why that is the case sometimes, but again, in psychology, the convention is to set that probability cutoff as 0.05. And so when we set our alpha at 0.05, what we're essentially accepting, right, is that if we were to run this experiment 100 times, right, and every time we ran it, we took a new sample. So if 100 times we took a new sample from the population, right, we ran the experiment every time, we got a new sample every time we ran the experiment, we're willing to accept a 5% risk that we're going to end up getting a significant difference between our sample mean and our population mean, just strictly based to random chance, based on dumb luck, based on selecting a sample from the tails of our distribution, an unlikely sample, right? So that our significant finding that shows a difference between a sample mean and a population mean is driven by chance and has nothing to do with the manipulation of our independent variable. And you have to accept some sort of risk for this, right? It's just, if you accept no risk, then you can't do any statistics, right? So the alpha, the conventional risk that we're willing to accept is 5%. And so we express that as an alpha of 0.05. Hopefully this makes intuitive sense to you. If I use one of these lower criteria, I'm accepting even less of a risk of getting a significant finding sort of based on random chance. And why do we do this? Well, the reason is that you can think of science as sort of small c conservative, right? In fact, our scientific reasoning really starts with this idea, right, having an assumption that we're not going to find an effect. I mean, certainly we hope that we do, right? I mean, it's the point of running an experiment is hoping to find an effect. But from a sort of professional point of view, from a non-biased, objective point of view, we start off with the assumption that the null hypothesis is correct, right? Meaning that there should be no difference between our sample mean and the population mean, right? So small c conservative here. Now, in order to demonstrate that we have an effect, right, if we really do, or if we run an experiment, we collect the sample mean, right, and that sample mean is different than the population mean, right? If we want to demonstrate that we have this effect, then we need to show that our result, right, the result of our sample mean, would be very unlikely to occur if the null is true. And if it does occur, right, well, that must mean that the null is incorrect, right? Especially meaning that if it hits our criteria, right, that it's an unlikely sample under the assumption that the null is true. So since the default position is that there's no difference between our sample mean and our population mean, then the criteria for which we will accept as a significant difference needs to be quite high, right? And this is where probability comes into play. Right, we need a clear understanding of what outcomes are likely if our null is true, right, that our sample means are close to our hypothesized population mean, and what outcomes are very unlikely if our null is not true, right? So our sample means are actually quite different than our hypothesized population mean. So if our null is actually true, right, the independent variable has no effect, then there are some samples that we would be considered high probability, and there would be others that we would consider to have low probability. So here's our old friend, the distribution of sample means, right, that we learned about back in chapter 7. So imagine all the possible plotted averages of means of some sample size sort of plotted in here and looking like a normal distribution. And this is what the distribution of sample means would look like, assuming the null is true, right? So remember from our last chapter, if we keep sampling from a distribution, right? Say we keep sampling from our groups of babies who took the new crawling vitamin. For every sample we took, we'd expect their mean to fall within this big middle section of our normal distribution. And if it did, right, if we took a sample of babies and we found that sample mean, if we were to plot it, fell somewhere in here, right, that would suggest that the null hypothesis is true, that there is no difference in when babies learn to crawl between the group of babies that took my medication compared to crawling age in the general population, right? After all, we know that some sample means have a high probability, right? The ones that are closest to the mean have the highest probability of occurring. So if we were to compute a z-score for a sample of babies, we start off by expecting that z-score is going to be somewhere close to the mean, right? Now, other sample means, they have a low probability of occurring if the null hypothesis is true, right? Low probability samples are going to be those that are located in the tail or tails, right? Depending if you have a one or two-tailed test. So if the null hypothesis is correct, right? If we operate under the assumption that the null hypothesis is correct, if we ran a z-test on a group of babies and they had a very high or a very low z-score, right? That's what they got, right? We ran an experiment and we found that the vitamin led to very late crawling ages or the vitamin led to very early crawling ages. So that's the truth that our data is telling us, right? Well, we would say that's an improbable sample, not an impossible, but improbable sample given our default expectation that the null is true, right? That there's no difference between the sample mean and the population mean. Well, again, we would normally expect the sample to fall in here, but if it fell over here, we would consider that a highly improbable observation, right? Under the assumption that the null is true. So what's that probability cutoff that I talked about earlier, right? Well, how do I find my cutoff z-score that I'm going to compare with the z-score I obtain by computing the test statistic? Well, again, in psychology, we tend to set our alpha level at a p less than 0.05. So sample means that have a probability of 0.05 or less, they're considered low probability or very unlikely if the null is true. The book talks about this idea that these sample means are so unlikely that if our null were true, we'd expect them to obtain them only 5 out of 100 times or less, right? We're also saying, right, there's sort of an inverse of this, right? There's an opposite of this. And what we're saying is that samples with a probability greater than 0.05, they're not that surprising. They have a high probability, right? And that's reflected here. This is in two tails, of course. You'd have half of that 0.05 over here. So you have 0.025 over here, 0.025 over here. And we would say these are, again, unlikely under the assumption that our null is true. That means that the remaining 95% is very, very likely under the assumption that the null hypothesis is true. The bottom line is that alpha levels allow us to make a decision about whether our sample data supports the null or the alternative hypothesis. And again, that's conventionally 0.05. There are some cases, 0.01, 0.001. Sometimes you might see pharmaceutical work or work using animal models that has that's testing some sort of maybe drug manipulation or gene therapy or something like that, where they set their alpha more conservatively to just be more cautious. But we're going to learn that sometimes this doesn't help; it hurts. And then we're going to put a 0.01 there. Come on, all right. Okay, so that 0.05, our alpha level, right? We can illustrate those ranges on a normal curve, right? And we're going to call the areas that are a boundary, right? The z-scores that form a boundary between the 95% of our distribution and the remaining 5% of our distribution. We're going to call those critical regions, or if it's a one-tailed test, you'll only have one critical region. But it's the area of the normal curve that contains extreme sample values that are very unlikely to be obtained if the null is true. So any sample means that fall into the critical region, they're low probability samples. So if we ran a z-test on a sample and it was either, really high, right, and it fell into this tail over here, or really low, like, I don't know, imagine a z-score of negative 2.30 or a z-score of positive, plus 3.10. It would fall in the tails of a normal distribution, right? In this case, we've got a two-tailed test going. And the probability of obtaining that sample mean would be less than that alpha level that we're using as our criterion, right? So these boundaries, these cutoff points, these z-scores for our critical region are determined by alpha level in the unit normal table. Once we decide on what we want our alpha level to be, or what proportion we want to use to define unlikely, we go to our unit normal table and we find the corresponding z-score or z-scores. So let's go back to this example here, right? A researcher predicts that children will learn to crawl earlier than the population mean after taking his motor development vitamin. Now remember, I told you that determining whether an example represents a one or a two-tailed test is important, not just for step one, for step two, because it actually determines whether or not we're going to be looking for 0.05 in one tail, or if we're going to have to divide that 0.05 in half and put 0.025 in the left tail and 0.025 in the right tail. So hopefully you recall from earlier, we determined that this was a one-tailed test. So once you determine whether it's a one-tailed test or a two-tailed test, if you determine it's a one-tailed test, you then have to determine which side of the distribution all of this 0.05 or whatever your alpha is, right? It'd be true if your alpha was set at 0.001, right? But you have to determine which side of the distribution, right, your alpha will fall in. And again, it should reflect the direction of the prediction. So if your prediction is a sort of is a less than prediction, well, really to make it quite easy, whatever your symbol, whatever your operator is for your alternative hypothesis in your alternative for step one, if it's less than, then all of your alpha is going to go on the left side of the distribution, and if it's greater than, all of your alpha is going to go in the right side of the distribution, right? So here's our distribution, right? If we have a one-tailed test, and our prediction is that our sample mean should be less than our population mean, which is, again, what this prediction is, right? That's what this alternative hypothesis represents. Our population mean should learn to crawl earlier than or less than this sample mean, right? So if it's less than our population mean, where might we divide the bottom 5% from the remaining top 95% of the distribution? Well, again, hopefully you said, well, this is a less than sign, and the professor just said less than means the whole 0.05 is going to go on the left side of the distribution. So I don't know, maybe somewhere around here, right? Maybe if I were to draw a line through this distribution, 5% of the scores would be to the left, and 95% of the scores would be to the right. And what I want to do is I want to find the z-score, right, that corresponds with 5% of all scores being to the left, and 95% of all scores being to the right. And if I'm starting with an alpha of 0.05, well, that's the proportion that I'm looking for in my unit normal table. I want to find the z-score associated with the proportion of 0.05. So the question I'll pose to you is, should I look for that proportion in the tail, the body, or mean to z? Hopefully you said the tail, right? Hopefully you said the tail, right? I'm looking for the value of 0.05. I'm looking for the proportion in the column for the tail that's closest to 0.05 without going over. And it looks like that proportion is 0.0495, and that corresponds with a z-score of 1.65. So now I want to go to my distribution, right, where I originally drew the line through the distribution that separated the bottom 5% from the top 95%. And I want to go ahead and label where that z-score is. And again, be careful here, because note that we're dealing with the left side of the distribution where all the z-scores are going to be negative values. So this 1.65 is really negative 1.65. And here's the deal. On step 3, when we compute our z-test, if that z-test is less than negative 1.65, then it means that it falls into our critical region, right? It means our sample mean is significantly different from our population mean. And it also means that it is an improbable, not impossible, but an improbable sample mean under the assumption that our null hypothesis is true. So therefore, we have to conclude that our sample is significantly different than our population. Maybe that's true. I don't know. We're not at that stage yet. All right, let's look at another example. A researcher predicts that his vitamin will have an impact on the age that children in his sample will learn to crawl compared to the population. Is this a one-tail or a two-tail test? Well, hopefully you recall from the previous example that this is a two-tail test, right? This is a two-tail test. So if we have a two-tail test, where would the boundaries be that represent the middle 95% of our distribution? And what I'm talking about here is we're going to now have two boundaries, right? We're going to have a boundary somewhere on this side and a boundary somewhere on this side. And those boundaries are going to represent the middle 95% of the distribution, with the combined 5% summing up to both of these tails, right? So again, I don't know without looking it up, but I'm going to guess that maybe it's somewhere around here, right? It's somewhere around here. And what we need to do is find the z-scores that correspond with this middle 95% in the unit normal table. And there's a couple of different ways that we can do this. It involves either dividing 95% by 2 or dividing the alpha by 2, right? If you divide the middle 95% by 2, then whatever that is, you're going to look for that value, right, that proportion in the mean to z column. If you divide the alpha by 2, right, in this case we're using an alpha of 0.05, then you're going to look for the value of 0.025, or again, whatever half of your alpha is, in the tail column. Find the value closest to 0.025 without going over, right? So, here's our values right here respectively, and we see that the z-score associated with these two proportions, again, whether you split the alpha in half and look for half of it in the tail, or whether you split the middle 95% in half and look for the mean to z, you're still going to get the same z-score of 1.96. Except remember, because it's a two-tailed test, you have two z-scores. So one of those is going to be negative 1.96, the other will be positive 1.96. And anything in here, in between these two values, represents 95% of the distributions. A distribution where the more extreme scores are represented in the tail regions. So now, when we compute our z-test, if it is less than negative 1.96 or greater than plus 1.96, right, that would mean our sample means would fall into the critical regions, and that would mean that our sample mean would be significantly different from our population mean. So there's some things that affect your likelihood of rejecting the null. So, for example, the smaller the alpha, right, the smaller the critical region. And that would mean the more extreme the critical value and the more conservative your hypothesis test would be, right? So the smaller your alpha is, the more conservative your test is. And that means that samples have to be even more extreme before they're considered low probability or unlikely, right? So note that if you set your alpha at a two-tailed test at 0.05, any z-score you compute that is less than negative 1.96 or greater than plus 1.96 would fall into the critical region, and they would be a low probability sample, and you would say, it's likely that our sample mean is significantly greater than or different than our population mean. But note, if you set your alpha at 0.01, right? So here's how we get these values. So let's take 0.001. If we divide that by 2 in a two-tailed test, and we look up that proportion, that whatever that is divided by 2 in the tail, we find that the z-score associated with that proportion is 3.30, right? So if we had a two-tailed test, we'd have a z-score of negative 3.30 and positive 3.30. And what that means is any sample that would be considered low probability or unlikely would have to be greater than plus 3.30 or less than negative 3.30. So the more conservative your alpha is, the larger the z statistic that you actually compute needs to be in order to say there's a difference between your sample mean and your population mean. All right, so again, now is the sort of point where I'd ask you if you have any questions. But if you do, just let me know via email or the course website. All right, let's move on to step 3, right? So step 3, we're computing our test statistic, right? This is a hypothetical, right? After you've clearly stated your null and your alternative hypotheses in step 1, and you've determined what your decision criteria will be based on whether it's a one or two-tailed test, and based on your alpha, then you're going to need to select a sample from your population. You're going to need to compute the relevant sample statistic, right? And again, here we're dealing, we're not actually collecting data in this class. We're pretending. But if you take a research methods class, even online, you might be involved in some sort of data collection. Maybe if it's just data collected from the class, but you probably likely be involved in doing some analyses of your own experiment. So what do we mean by a test statistic? A test statistic. Well, it's a single value that describes our sample. We're going to use that to test the hypothesis. It's the result of our statistical test. So if we ran a one sample z-test and that z-score was plus 2.01, then plus 2.01 is our test statistic, right? Soon we're going to talk about several different test statistics, because there's a different test statistic for each type of hypothesis test that we're going to learn, right? We've got Z statistics that we're dealing with now, and soon we'll transition to T, then ANOVAs, and then Rs, and so on and so forth. But for now, we're going to go over what we know, which is a Z-score for sample means. And lastly, look at this bullet that I have up here. I just want to talk about this idea of a statistical test essentially just being a ratio, right? And hopefully it'll start to become apparent that every test that we learn in this class is a ratio, right? Meaning that our numerator is always going to be some sort of obtained mean minus a hypothetical population mean. And we're always going to divide that difference by some sort of error term, right? Some sort of error term. And look, here's our good friend, the Z statistic, right? Our sample mean minus the population mean divided by an error term. In this case, it's the standard error of the mean. Every statistic that we learn is going to be sort of a variation on that. There'll be different things we plug in and different ways that we define these terms, but it's always going to be some obtained difference divided by some sort of measure of variance, right? Now, here's our statistic. Again, we'll fill in some numbers here in a minute. I just want to remind you of the formula for our Z-scores for sample means, right? This is our formula for a one sample Z-test. So again, your obtained difference divided by the difference expected by chance, in this case, the standard error. So in our numerator, we've got an obtained sample mean, right? This is the mean that we collect in our experiment. From that, we're going to subtract some sort of hypothesized population mean. And in the denominator is our standard error, right? That's the standard deviation divided by the square root of our sample size. So again, it's the standard difference that we can expect by chance between our sample mean and the population mean. And based on the results of that, at step 4, we're going to make a decision, right? So now we've run our statistical test. We've got a Z-score for our sample. Step 4 is using that test statistic to examine whether the sample falls in, where it falls in the hypothesized population, right? So we're simply comparing our Z-score, right, that we got from running our test in step 3 to the critical value Z-score or Z-scores, if it's a two-tailed test, that we got from our unit normal table. And so the probability of getting this sample, if the null is true, is going to lead us to make one of two decisions about the null hypothesis. Either we reject the null hypothesis or we fail to reject the null hypothesis. So if our test statistic falls within the range of our critical value, right, our critical region, then we would reject the null hypothesis. This means that the data supports the conclusion that our alternative hypothesis was correct, right? It means that there's a difference between our sample mean and our population mean. If it falls between the range of our critical values, or if it's a one-tailed test, if it just simply falls outside of our critical value range, then we would fail to reject the null hypothesis. This means that the null hypothesis was correct, right? There's no statistical difference between our sample mean and our population mean, right? So reject the null, reject the null. The test statistic is more extreme than the critical value. It falls within the critical region. The alternative is supported. There is a significant difference. So the obtained difference between our sample mean and the hypothetical population mean is quite large, right? Larger than what we would expect by chance. And it's a low probability sample if the null were true. Right? It's unlikely we would get these results by chance. So we have evidence that our treatment, in fact, has an impact. And then we have the fail to reject the null hypothesis. So this means our test statistic is less extreme than the critical value, right? It does not fall in the critical region. Therefore, our null is supported. There is no significant difference. So now we're saying the obtained difference between our sample mean and the hypothetical population mean is not much larger than the standard amount of difference that we would expect by chance. So this is a high probability if the null was true, right? There's no evidence that our treatment has an effect. So any differences between the sample mean and the population mean are strictly due to chance. And I want to note here at the bottom, right, that if we reject the null hypothesis, it doesn't mean that we've proved something. For myself and maybe a lot of other professors who've we've had or maybe we'll encounter that are sort of very serious about science, right? The idea of proving something with an experiment is sort of it kind of makes our hair sort of stand up on end. Because if we reject the null, all we're essentially saying is that right now at this particular moment in time, our sample mean provides sort of the best evidence of a difference, right? Science is an iterative process, right? This falls under the idea that science is small c conservative. And what we accept today based on evidence can certainly be different tomorrow. It doesn't mean that we've done anything wrong or that we've been, we've lied or something like that, right? We've been dishonest. There are plenty of good reasons as to why our interpretation or our understanding of some phenomena changes over time. The biggest thing can often be technology. I do a lot of brain imaging work using EEG. I've been at it for a dozen years now, right? And in that time period, which is very small, in that time period, I have seen our ability to improve our methods of analyzing EEG data dramatically improve, right? Dramatically. It has changed in leaps and bounds over the last 12 years. And as a consequence, certainly that change that has been validated through many experiments can certainly cause us to rethink previous results, right? Or trying to replicate previous experiments using sort of a new analysis methodology can lead to maybe different conclusions or maybe extensions of these conclusions. So we don't prove anything. All we're left with after we run an experiment is the best evidence that we have right now for something, right? Science is iterative and things change. I know we think about some things in terms of settled science and consensus, and I'm not trivializing that, but science really improves, science really progresses when there's disagreement, right? When everybody agrees, then there's really no phenomena to explore. And I will say that few things are like gravity. Like gravity you can trust. You can hold a pen up and you can drop it and it's going to fall to the ground every time. There are a few things in science that meet that level of a law. Anyway, once again, period of time where I'd ask you if you have any questions. Okay. I don't know. This is not the worst time to stop and pick up later. We pick up with some examples here. I don't know. Maybe soldier on through one example. That's a good idea. So forget what I said. Don't stop the video yet. Let's do one example, at least going through the first 4 steps. And then it's a good time to take a break and come back and watch the video on the next scheduled day. Okay. Our good old baby crawling data, right? So we have these age when infants learn to crawl. The known parameters are 35 weeks, right? That's our population mean with a population standard deviation of 3 weeks. And what we're asking here is, does our vitamin impact crawling age, right? So that's our scenario, right? Very sparse, but believe it or not, there's enough for you to do this. And believe it or not, I want you to give it a try, right? I want you to do the first 4 steps of hypothesis testing on your own, right? So in other words, determine whether or not this is a 1 or 2-tailed test, state the null and the alternative hypotheses, determine a decision criteria using an alpha of 0.05, right? So draw a normal distribution, plot where that is, find the z-score at an alpha of 0.05 in your unit normal table. Then I want you to go ahead and run this statistic, right? So we've got a sample size of 49 with a sample mean of 34 weeks. And based on the results of your sample statistic, determine whether or not it falls within your critical region or it falls outside of your critical region, and simply make a decision where you either reject the null or you fail to reject the null hypothesis. So go ahead and pause the video. You should be at this for, I don't know, maybe 7 to 10 minutes would be my guess. So once you've done these 4 things, you've gone through the 4 steps, then come back to the video and I'll show you how I did it. Okay. So we want to state the null and the alternative hypothesis. Is this a 1 or a 2-tailed test? Well, It says, does the new vitamin impact crawling age? Hopefully you noticed that there was no directional prediction here, right? Again, it's just asking whether or not it impacts crawling age. It could improve crawling age, or maybe in some ways it could impair crawling age. Who knows, right? There is no a priori prediction. So that means that this is a two-tailed test. It's a two-tailed test. And like I said, when you're stating the null and the alternative hypothesis for a two-tailed test, the operators that you use to separate the sample mean from the population mean is an equal and not equal sign, respectively. So this is what it should look like. It's a two-tailed test, and your null hypothesis should have been that the mean age of our sample should be equal to our population mean of 35 weeks, whereas the alternative should be that the mean age of our sample should be not equal to our population mean of 35 weeks, right? And that's all there is to it. So two-tailed test, and your operators should be equal and not equal, respectively. And again, don't forget all the little, seemingly trivial things here, right? The H subscript 0 colon, all of that stuff is the correct way of stating your null and your alternative in statistical notation, and it is something that you have to do. Typically stating the null and the alternative is worth 2 points. If you made a little mistake here, would I take off 2 points? No, but you still uselessly lose, fractions of points that you don't need to give up, right? So this isn't a guideline, or it's not a suggestion. It's a rule, right? So you just want to replicate exactly what I'm doing in the slides. Okay. Step number 2 is we want to determine the decision criteria, right? So what was our alpha? Was this a one or two-tailed test? And based on the alternative hypotheses, where are we putting our critical region or critical regions, right? Well, I'd already stated in the beginning that our alpha was 0.05, and in the homework, the alpha should always be stated, but if it's not stated explicitly, then you should treat the alpha as if it is 0.05, which is sort of the default alpha. But I should be explicitly stating what I want you to use. And also beware, even though the conventional alpha is 0.05, don't be surprised if on the homeworks or in an exam, I give you a scenario where you have to do some math or do some sort of interpretation with the alpha being something other than 0.05. But in this case, we set our alpha at 0.05. Now, is this a one or a two-tailed test? Well, we'd already determined that it was a two-tail. And then based on the alternative hypothesis, which was a not equal sign, where does our critical region or regions go? Well, here we're going to have two critical regions, and we're going to split that alpha of 0.05 in two. So we're going to have 0.025 in the left tail and 0.025 in the right tail. And hopefully the next thing you did was sketch a curve, right? That sort of allowed you to kind of state where you would expect the middle 95% of the distribution, so these boundaries to be. And from there, if you divide 0.05 by 2 and look for 0.025 in the tail, you'll find the corresponding z-score is 1.96, which means that the z-scores that are the boundaries for our critical region, or say the z-scores that are the boundaries for the middle 95% of our distribution, are negative 1.96 and positive 1.96. So again, if we compute our z-score in step 3, if it falls into these critical areas, then we would reject the null. But if it falls in this big 95% region, we would fail to reject the null. And this also should be sort of becoming pretty obvious for you. It's like, oh, wait a minute. If my alpha for a z-test is 0.05 and two tails, then my z-scores are always going to be negative 1.96 and positive 1.96. Or alternatively, if my alpha is all in one tail, if it's in the left side of the distribution, my z critical value is going to be negative 1.65. Or if it's in the right of my distribution, my z-score is going to be positive 1.65. Again, that's something that the more you do these, it'll be obvious. You'll sort of commit it to memory. And it's easy in z-scores. Unfortunately, it gets a little bit more complicated when we move on to the next chapter when we do t-tests. But, for now, you can even commit that idea to memory in z-scores and it's kind of useful because you don't necessarily need to be looking things up in the table all the time. Anyhow, step 3 is to compute the statistic, right? So we're going to, in other words, collect the sample, right? So collect our data, compute the test statistic, and then run the statistical test. So what it means is we're going to run a z-test and compare it to a population mean. And here's the data that we have, right? So our population data was a mean of 35 weeks with a standard deviation of 3 weeks. Our sample mean was 34 weeks, and we had a sample size of 49 babies. And here's our formula, right? So you should have just simply plugged everything in here. The sample mean is going to be 34. The population mean is going to be 35. And we're going to divide that by the standard error of the mean, which is our standard deviation of 3 divided by the square root of our sample size, which is 49. So, I think it's easier to break this up into 2 parts. The first is to compute the standard error of the mean first, right? So here I'm doing it sort of easily right here without sort of writing it out. But our standard deviation was 3, right? We're going to divide that by the square root of our sample size, which is 49. This is how you'd enter it into your calculator. And we get a standard error of the mean of 0.429. So this value is going to be the denominator of our test statistic, which is the next step, computing our z-score. We're going to take the sample mean minus the population mean, so 34 minus 35, and divide it by the standard error that we computed at the previous step. And that's going to give us a z-statistic of negative 2.33. And so now we need to make a decision, right? We need to make a decision. What we really need to do is plot the results of our z-test. And if we were to plot that negative 2.33, it would fall over here on the left side of the distribution. And what you ask yourself is, does it fall in the critical region? This is one of the reasons why plotting these little figures is so useful, because it gives you a good visualization. Remember the rule: if our obtained z-score fell in this area or this area, then we would reject the null, right? It means that it falls in our critical region. And if we reject the null, if it falls in our critical region, right, then we reject the null hypothesis. And what we're essentially saying is that there's a significant difference between our sample mean and the population mean. So that means our sample of babies was different than our population mean. And this would be a highly improbable sample mean under the assumption that the null hypothesis is true. Okay. Pause the video. Take a break. Come back to this on, let's see, you should be watching this Thursday. So you'll watch the second part of this video on next Tuesday. That's my advice. Or you can power through, or you can watch it whenever you want. You can, but break this up. Think about it. Work a little bit on the homework. Do the things that you can, right? Then come back to the video and learn some more, and then do some more things on your homework, and so on and so forth. Don't feel the need. This is why this is sort of a semi-scheduled class, right? Because statistics is hard enough without you trying to sort of cram it all into kind of one day. So, take a break. All right. And this is where you should be coming back. Let's do like a mini experiment here, right? You can, if you have a stopwatch, time yourself, right? So you can use your phone or whatever, right? But what I want you to do, and maybe you've heard of this task. It's something we call the Stroop task. We use it a lot in cognitive psychology. I'm going to show you a slide right on the next screen, and I want you to read the words on the screen in order as fast as you can. So when I say go, right, I'm going to count to 3 and say go. Turn on your stopwatch and read the words on the screen in order as fast as you can. So 1, 2, 3, go. Okay, so hopefully you stopped the stopwatch and wrote down how long it took you to read these list of words. All right, I want to do this again, but now instead of reading the words, I want you to say the ink color of the word on the words on the screen in order as fast as you can. So again, on count of 3, I'm going to say go. It goes. Start your watch. State the ink color of the words on the screen in order as fast as you can, and then stop the watch when you're done. 1, 2, 3, go. It's much harder, right? It's much harder. That's something that we call the Stroop task. Again, maybe you've heard of it. It's a task that we use to test things like attention and cognitive control. And you're slower for what we call congruent trials. So let me go back. Or incongruent trials. I'm sorry. An incongruent trial would be a trial in which the name of the word, right, and the ink color of the word differ, right? So this is the word yellow, but it's written in green ink. A congruent trial would be where the name of the word and the ink color match. So here's the word red written in red. And so you're slower for these incongruent trials than you are for congruent trials. And it's because we get this effect where when you see a word, you can't help but sort of read it, right? So you're not seeing YELLOW. What you see is yellow, right? All these words in this combination activate the constituent representation of the word yellow. And when you read it, it's almost automatic. Like you have to inhibit yourself from doing that, right? So when you have to name the ink color instead of state what the word is, you have to inhibit this process of where you want to say yellow, right? Because you have this natural inclination to read words, and you inhibit it, and you're able to say, oh, green, right? Because that's the color of the word. And people can do this, and they can do it quite well, right? At a 95% accuracy rate. But what we see is that they're dramatically slower for incongruent trials than congruent trials, right? And so this is from a real paper. These people got this idea that, well, if we can hypnotize people into not seeing these as words, but seeing them as symbols, right? If they could see these words as symbols, then the word wouldn't activate itself, right? These letters wouldn't activate the constituent word. And as a consequence, people should be much better on these incongruent trials. In fact, there should be no difference in performance on incongruent trials compared to congruent trials if you could be hypnotized into thinking, well, these aren't words, they're symbols. Now, I will say, I think they found an effect. I thought the research was silly. You could look it up if you're interested, mostly because of the sort of issues of bias and hypnosis. But anyway, I just wanted to do this because I think it's a cute little example. So here we've got reaction times to these incongruent Stroop trials. And we've been doing the Stroop since the 60s, right? So we know that the average time to respond to a Stroop trial is 720, or incongruent Stroop trial is 720 milliseconds. With a standard deviation of 110 milliseconds. And the question we're asking here is, can hypnotic suggestion reduce reaction times on incongruent Stroop trials? So just like when we left off, I want you to do these 4 steps again, right? And so pause the video. You've got everything you need here to state the hypotheses, determine the decision criteria, compute the statistic, and then make a decision. So pause the video, give it a try, and when I come back, I'll walk you through how I did it. All right, so step 1, state the null and the alternative hypothesis. Well, first we need to determine, is this a 1 or a 2-tailed test? And hopefully you said it was a 1-tailed test, right? Because the prediction here is, can hypnotic suggestion reduce reaction times? Reduce. So we're predicting here that our sample mean is going to be some value less than this population mean of 720. So as a 1-tailed test, if our prediction is less than, then our alternative hypothesis, the operator for alternative hypothesis, should be a less than sign, and indeed it is. So H subscript 1 colon mu reaction time. So the mean reaction times for our sample should be less than 720 milliseconds, which reflects the reaction time data for our population. Our null hypothesis, H subscript 0 colon, our mean sample should be greater than or equal to 720 milliseconds. And here we're essentially saying, look, our sample mean should not be different than our population mean, whereas our sample mean should be less than, right? Faster than. They should be faster for incongruent trials under hypnosis than what we see in the population data. And now we need to determine the decision criteria. So we'll set our alpha at 0.05. We already established it's a 1-tailed test. And based on this, based on the alternative hypothesis, where should our critical region go? And here we're only going to have a single critical region because it's a one-tail test, right? So 0.05, one tail. And because it's a less than, right, less than sign, that means all of our alpha is going to go to the left of the mean in our distribution. So all the 0.05 is going to go on the left side. So again, we'll start by sort of just sketching a curve and putting a line through where we think 5% of the distribution falls to the left and 95% of the distribution falls to the right. And what we're looking for in our unit normal table is the proportion closest to 0.05 in the tail without going over. And when we do that, again, we've done this already, we see that proportion is closest to 0.05 without going over is 0.0495, and that gives us a z-score of 1.65. But again, because we're dealing with a z-score, a z-critical score that's in the left side of our distribution and the negative side, our true critical value here is negative 1.65. So again, when we run the statistics, if our obtained z-statistic falls in this critical region, we would reject the null hypothesis. We would say this is an improbable sample mean under the assumption that our null is true, right? Or if it falls into this region, right, into the big 95% region, we would fail to reject the null. We'd say, well, that's not an improbable sample. It's likely that sample mean was just any differences that exist are just strictly due to chance. Okay, now we need to collect our sample, right? We need step 3, we need to compute our statistic. And here's all the notable data, right? So this is everything that we need. We've got our population parameters. We've got our sample data. So we're going to start with that sample mean of 680, subtract that from our population mean of 720. And whatever that difference is, we're going to divide that by our standard deviation, which is 110, divided by the square root of our sample size, which is 35. And first things first, I like to just compute the standard error of the mean, right? So here's that formula, and we remember these values from the previous step. So it's going to be 110 divided by the square root of 35. That's going to give us a standard error of the mean of 18.59. So remember, this value is going to go in the denominator of our z-statistic, which is what we can compute now. So here we've got our sample mean of 680 minus our population mean of 720. We're going to divide that difference by our standard error of the mean. And we end up getting a z-statistic of negative 2.15. And so now we need to make a decision here, right? So here's our original distribution with our critical value and our critical area plotted out. And what we want to do now is plot the results of our z-test. So that z-score of negative 2.15 is probably somewhere over here. Importantly, it falls in the critical region, right? If it falls in the critical region, then we reject the null hypothesis, right? Okay, great. Look, if there's anything that, you found confusing or you didn't understand or you got something different than I got, then go ahead and go back in the video and watch it again, right? And make sure that you understand it. It's important that you get this because these are going to be concepts that we really continue to build on, these 6 steps of hypothesis testing, even though we've only done 4. Again, these are going to be concepts that we build on, so you want to make sure that you're as comfortable as possible with this so that the other stuff is a little bit easier to wrap your head around. All right, another example, our RAD score, right? We had a population mean of 60, a standard deviation of 14, and we're asking, does intervention reduce the potential for depression in adolescence? So again, I want you to go through the same 4 steps. Warning though, a little warning right here. Note I'm setting the alpha at 0.001. So keep that in mind as you're doing these steps. So go ahead and pause the video and I'll show you how I did it when you come back. All right, so state the null and alternative. Is this a 1 or a 2-tailed test? So again, it looks like we have a directional prediction here, right? Does intervention reduce the potential for depression in adolescents? So in other words, the researcher is predicting that her sample data should be less than the population mean of 60. Again, it could be 59, 58, 2. Who knows? We don't know. But the prediction is it should be less than. Reduced suggests less than, right? Less than, our sample should be less than the population of 60. So there you have it, right? Again, I think the strategy is to do the alternative hypothesis first, because that's most reflected in the example. So H subscript 1 colon, mu rad scores should be less than the population mean of 60. Then stating the null hypothesis is just simply reversing this operator and then adding the equal sign. So our null hypothesis is that our mean rad scores for our sample should be greater than or equal to 60, right? So in other words, there's no difference, or the intervention reduces rad scores alternatively. Now we want to determine the decision criteria, right? So I'll just move to the next slide. Our alpha here was 0.001, right? So we have a new alpha. And this is a one-tailed test, right? And remember, the alternative hypothesis was the operator was less than, right? So if it's less than, that means all of our alpha for a one-tailed test is going to go on the left side of the distribution. So now we need to find, again, you draw a normal distribution and you put a line through where you think 0.001, right? The dividing point where 0.001 is to the left side of this division point, and then the remaining 99.999 or whatever, some ridiculously high amount is on the falls. All those scores fall to the right of that particular score, right? So we don't need to divide anything by 2, since all of our alpha 0.001 is in the left side of the distribution, so it's in one tail. So we're looking for a value of 0.001, or a value that's closest to 0.001 in the tail without going over. And this is an interesting challenge. I'm curious to see whether or not you got it correct. Obviously, only you can answer. But note how there's 3.001 proportions. So how do you choose which one to pick? Well, the convention is that you choose the one that's the most conservative. I mean, this means there's very little difference between 3.08 and 3.10, practically no functional difference. But regardless, the criteria is that you select the one that would be the most conservative. In this case, that would be 3.10. 3.10 is just marginally more conservative than 3.09 or 3.08. But so anyway, pick the most conservative one, and then you would label that on your distribution, right? So negative 3.10, because everything's on the left side of the distribution. So in other words, if you get a sample that falls into this critical area, then by default the sample has to be less than negative 3.10, and it would be a highly improbable sample under the assumption that the null is true, and you would reject the null. But it's much more highly probable that your sample should fall above negative 3.10, which in that case we would fail to reject the null hypothesis. All right, so we've collected data, so let's run the statistic, right? Here's all our population parameters and our sample data. And first, let's do the standard error of the mean, right? So we're going to take the standard deviation of 14, divide that by the square root of our sample size, which is 15, and that's going to give us a standard error of 3.615. So that's going to be the denominator of our test statistic. And we're going to take the sample mean minus the population mean. So that's 54 minus 60. Divide that by our standard error of the mean. And we get a test statistic, a result of negative 1.66. So now we need to make a decision, right? So here's our distribution with our Z critical score plotted. We know our critical area. We know the big area that we would expect expect the sample to fall. If we plot it, well, there it is roughly, right? Negative 1.66. Does it fall in our critical region? The answer is no. Therefore, we, fail to reject the null, right? We fail to reject the null. In other words, there is no significant difference between our sample mean and our population mean. All right. So any questions so far? Well, ask me if you do. Here we've gone through all 4 steps of hypothesis testing. Now I want to switch gears a little bit, and I want to talk about steps 5 and 6. But again, this can also be not the worst time to sort of pause, right? This would be a good time maybe to jump to the very end of the video, see some of the practice problems I have, maybe give a shot at doing some of those. We've performed a few Z statistics now for steps through 1 to 4. And again, you want to be sure that you understand this, that you've got your head wrapped around this, right? We failed to reject the null here. Make sure you understand why, right? Why? Oh, well, this is the statistic we computed. If it would have fallen in here, right, if it would have been less than negative 3.10, then we would have said there's a difference between our sample mean and population mean. But there didn't. It fell over here, right? It fell on sort of the high probability sample range. And therefore, we would fail to reject the null. We'd say there is no difference between our sample mean and our hypothetical population mean. So make sure that you're really comfortable with those things before moving on here. And if you are and you want to just plow through, okay, knock yourself out. But if not, this is as good as any time to stop, do some practice problems, maybe reread some things in the book. Watch some things over again on the lecture, if you're not 100% comfortable, and then go ahead and finish up this last remaining part on will be Thursday, I think, right? Day 3 in the syllabus of chapter 8. And I should say, so the way I have these things broken up is that they tend to go a little bit more slowly. Of course, shouldn't be surprising when I'm teaching this in person, right? Because people tend to have more questions about how things are done and so on. Okay. Anyway, now I want to talk about steps 5 and 6, right? If appropriate, compute effect size, and then state our results in APA format. Okay, here's a scenario. Flu shot A costs $25. Flu shot B costs $40. And both have been shown to produce a statistically significant reduction in risk. Which one of these would you choose? Now, let's assume that we ran hypothesis testing on both of these flu shots, right? And we found in both instances you can reject the null hypothesis. So whether you get flu shot A or whether you get flu shot B, they reduce flu rates compared to not getting a flu shot, right? So they both work, right? Flu shot A is $25. Flu shot B is $40. Which one would you pick? Well, most students say flu shot A. Okay. But what if flu shot A reduced the risk by 20% and flu shot B reduced the risk by 75%, right? And again, I want to reiterate this idea. If we tested each of these flu shots against people who didn't get a flu shot, each test would lead to the same conclusion with the hypothesis test, right? We would reject the null. But obviously, there's an important difference between the two, right? One of them, flu shot A, reduces the risk by 20%, where flu shot B reduces it by 75%, right? So even though it's a little bit more money, the magnitude of its effect is larger, right? So this is an important idea here. Computing a test statistic tells us whether or not there's a difference between our sample mean and a hypothesized population mean, but it doesn't tell us how big that difference is. And that's important information, right? So if and only if we reject the null hypothesis, then in order to determine the magnitude or the size of the effect, we compute the effect size. And why do we do this if we reject the null? Because it's useful to understand not only whether or not the effect is significant, but how big that effect is, right? So the effect size is a measure of the magnitude or size of the treatment effect. It's not a measure of how significant it is, right? In experimental research, effect size answers the question, how big is the impact of the independent variable on the dependent variable? And we always and only present our effect size when we have significant results. That is, we only compute and present effect size when we reject the null. If we fail to reject the null, we don't have an effect. There is no significant difference between our sample mean and our population mean. Therefore, we would not compute an effect size. In fact, if we were answering this on homework or an exam, and if at a prior step we failed to reject the null, and then it asked us later on in the question, what is the effect size? The only correct answer would be, NA, not applicable, NA. We only compute and report effect size when we reject the null. Now, there are a lot of different measures of effect size. Here, we're going to learn one for now. As we learn additional statistical tests, we'll learn different ways to compute the effect size. But here we're going to do something called Cohen's d. This is the standardized mean difference, and it should look a lot like a regular z-score, except instead of a raw score up here, we've got the population mean minus the sample mean minus the population mean divided by the population standard deviation. And there's two things I want to note. First, report it out to 2 decimal places, and always report it as a positive number, even if you computed it and it was a negative number. Report it as a positive number. In other words, we call that its absolute value. Report the absolute value of Cohen's d. So remember, we had an effect for crawling age, right? In other words, there was a significant difference between our sample mean and our population mean. So therefore, it would be appropriate to compute the effect size. And let's do this really quick. Here's a reminder of our formula, right? Our formula is the sample mean minus the population mean divided by the population standard deviation. So that's going to be 34 minus 35 divided by 3. That's going to give us negative 1.33 or negative 0.3333 and so forth. But remember, round to 2 decimal places and report Cohen's d as an absolute value. So d equals 0.33. This one I want you to try yourself. We had an effect for this as well. Remember, people that were hypnotized were faster for incongruent Stroop trials than the people we have for the general population on incongruent Stroop trials. So remember your formula from the previous slide and try computing the effect size. So pause the video, compute it, and I'll give you the answer when you come back. Oops. Yeah, here we go. Right, so the sample mean minus the population mean divided by the population standard deviation. So negative 40 divided by 110 is going to give us negative 0.3636. So again, round to 2 decimal places, report as an absolute value. So Cohen's d in this case is 0.36. And what about the rads? Do we compute effect size here? No. Why? Because we didn't get an effect. It wasn't significant. Remember, our critical value had to be something less than negative 3.10, if I recall correctly. And the statistic that we computed was negative 1.66. So our test statistic did not fall in our critical range, critical region. So we would fail to reject the null. It means we have no effect. It means that the mean RAD scores for the sample were not significantly different than the population, and therefore we don't compute an effect size for that. So if we were, again, facing this on a homework or an exam, our correct answer would be NA, not applicable. All right. What about interpreting this, though, right? There's sort of 2 ways here, and we'll talk about it in terms of our baby crawling data as well as our Stroop data. So one thing you could do is take that effect size and multiply it by the standard deviation, and it'll give you, in the same units as you've been working with for the whole time, right, as you started with, it'll give you the exact magnitude of the effect, the actual value of the effect, right? So in this case, if we were to multiply the effect size by the population standard deviation, we get an effect of a week, right? A week. So our vitamin improved baby crawling age. The effect of that improvement was 1 week of performance. The more common way of interpreting Cohen's d, though, really is by interpreting it in light of this table. So anything that falls from 0 to 0.2, we'd consider that a small effect. Anything between 0.2 and 0.8, we'd consider a medium effect, and anything above 0.8, we'd consider a large effect. And just for your own sort of point of reference, in psychology, if you get an effect size of 0.40, even though that's a medium effect, it's a pretty robust effect. It's a very good effect size. It's a very decent effect size. There's another thing I want you to take note of here, and that's the idea of statistical compared to practical significance. So here, we get a medium effect, which is great. We rejected the null, which is fine. But note here that our actual effect is only 1 week. Okay. Now, remember this scenario. We have babies. We're giving them some sort of experimental vitamin and seeing the effect that it has on motor development. All right. Well, we didn't know the magnitude of the effect at all before we got into this, but now we know that effect is really only 1 week. And so, I don't know if any of you are parents, but you don't have to be to answer this question. Do you think that you'd hand your baby over to a team of scientists to pump full of a experimental vitamin, and it's only going to net you a 1 week improvement in crawling time? Well, probably not, right? So even though it was statistically significant, right, sometimes we need to look at our data as we're interpreting it and ask ourselves, well, is it practically significant, right? I think another interesting example in this idea of practical versus statistical we can think about in terms of Stroop. Okay, now look, we get a 40 millisecond effect. And note that it's a medium effect, right? So it's a nice effect for a psychology experiment. Now, once again, you might think, well, gosh, 40 milliseconds, that's nothing, right? And on the surface, I'm inclined to agree with you, right? 40 milliseconds, we can't even fathom what 40 milliseconds passing in our life feels like. But think about what we're studying here in this experiment, right? We're studying the cognitive operations of attention and cognitive control. And if you think about how fast neurons fire, right, which is incredibly fast, then a 40 millisecond effect is actually quite robust, right? 40 milliseconds when it comes to neural communication, it's like an eternity, right? So not only is it statistically significant, but the effect, at least in this data that we're playing with, shows that hypnosis is practically significant, right? It really does lead to a robust improvement, particularly if we're thinking about this in terms of neural processing, compared to non-hypnosis, right? So the size of the number, don't let that sort of be your guide here. You have to sort of think about what's going on sort of qualitatively in your experiments as well when it comes to interpretation. All right, step 6 would be to state your results in APA format. And there are 3 defining characteristics that you need to get right, 3 things that you need to get right in order to get full points on this. The very first sentence that you should write should be a statement of whether or not you rejected or failed to reject the null hypothesis. This should be followed by the test statistics, the p-value, which is something that reflects our alpha, right? It's going to be our way of stating whether or not we rejected or failed to reject the null. And if we ended up rejecting the null, you should report your effect size. So that's the second thing. And you want to be careful. When you report your test statistic, you're reporting the results of your test statistic. You're not reporting the t critical value that you looked up in your table. And then finally, after you've stated what the statistics are, the third thing you need to do is describe the differences between means in very clear, formal, and direct language. And if you have them, you should always report means and standard deviations. Okay. So let's look at an example with the baby crawling data, right? So the very first thing we need to write down is we reject the null hypothesis, because that's what we did, right? If we failed to reject, then that's what we would have wrote. But because our test statistic fell into our critical region, we rejected the null. The very first thing we need to write down to get full points is we reject the null hypothesis followed by a comma. Then we want to report our test statistic, and here, in this case, it was the z statistic. So z equals negative 2.33, because that's what we computed, right? Then we need to report the p-value. Now, if we reject the null, right, what we're going to report is p less than whatever our alpha was. So when we reject the null, it's p less than whatever our alpha was. If we fail to reject the null, there are two ways we can report that APA is fine with. We could say P equals NS, right? That means P equals not significant. Or we could report P greater than 0.05, right? So it doesn't matter. Now here, because we rejected the null, after we state our p-value in the direction of the p-value, we put another comma, and then we need to report the results of our effect size. So in this case, Cohen's d equaled 0.33. And note that if you only have to worry about this if you're typing this out. Your z, p, and d letters should all be italicized. Anyway, so you report the z statistic, report the p-value, report Cohen's d if appropriate, and that's followed by a period. Then there's some sort of statement, right, of which you compare your sample mean to your population mean. So here we're saying something to the effect of infants who took the vitamin, and note that that's the level, that's our factor here, right? And as soon as we state what that is, then in parentheses we need to report its respective mean and standard deviation. Well, here I didn't give you the sample standard deviation. All I gave you was the mean. So that's all you can really report. So we say infants who took the vitamin and their mean was 34. We state that in parentheses. Learned to crawl earlier than the population average. And there's the population mean and the population standard deviation in parentheses. Again, the Greek letters and the English letters, if you're typing this, should all be italicized. Here's our data for Stroop. Again, in this particular experiment, we found a significant difference between our sample mean and our population mean. So it's appropriate, our decision would have been to reject the null hypothesis. So again, that's the first thing. If we're writing those results up in APA, that's the very first thing we need to write down. We reject the null hypothesis, followed by a comma. We report the z statistic. The z statistic was negative 2.15. Our alpha level was 0.05. We ended up rejecting the null, right? So we're going to say p less than 0.05. And then because we rejected the null, we need to report the results of our Cohen's d, which is 0.36. And then finally, the third thing is we need some sort of statement that illustrates the difference in means. So participants who experience hypnotic suggestion, and we report their mean, right, the sample mean of 680, were faster during incongruent trials than the population average. And there we report the population data, right? The population mean and the population standard deviation. Now you might recall that on the RADS example, we failed to reject the null, right? So that's the very first thing we should write. We failed to reject the null hypothesis, followed by a comma. Z equals negative 1.66, right? That's the statistical test we ran. And then I follow that with a comma. P equals NS. Again, you could say P greater than 0.05. I just typically use the convention of P equals NS. And note what's missing here, right? No Cohen's D, right? Well, it would be inappropriate to report the effect size here because we have no effect, right? We found no difference between our sample mean and our population mean. Therefore, we would not compute an effect size, right? We still need to have some sort of descriptive sentence, though, and that descriptive sentence should reflect that there was no difference between our sample mean and the population mean. So here I've written participants who experienced the intervention, and then that's the sample, so I report the sample mean, were not significantly different than the population average, and then I report the mean for the population and the standard deviation. I want to illustrate a couple of interesting things here. Our alpha and our sample size affect our likelihood of rejecting the null hypothesis. So let's sort of have a little bit of a thought experiment here, right? What if we increased our alpha from the very conservative value of 0.001, which is what we started with, to 0.05, right, which is the conventional alpha in psychology. Now recall, we failed to reject the null at an alpha of 0.001. Let's see what would happen, right, if we weren't so conservative, right, set that at a conventional alpha of 0.05. Would we reject or fail to reject the null? Well, remember, this was a one-tailed test, alpha of 0.001, a z-score of negative 1.66. This was all in one tail, so if we find the value closest to 0.05 without going over, we know from the previous examples it's 0.0495. That gives us a z-score of 1.65, right? Or really, it would be a z-score of negative 1.65. would we reject or fail to reject at an alpha of 0.05? Well, remember, our original z-score was negative 1.66. That's less than our new critical value, right, at an alpha of 0.05 of negative 1.65. So we would reject the null hypothesis. So for the same exact scenario that we ran for our RADS score, right, for our RADS test, we would fail to reject the null if we had the criteria set so conservatively at an alpha of 0.001. However, we would reject the null if we had set our alpha at a more conventional level of 0.05. And so this becomes very interesting, right? Because if we reject the null, that means we have an effect and we compute the effect size, right? And if we do that, here's what we get, right? If we take the sample mean minus the population mean divided by the population standard deviation, we get an effect size, a Cohen's d of negative 0.428. And if we round it appropriately and report the absolute value, we get a Cohen's d of 0.43. Now let's think about this in terms of interpretation. If we multiply that effect size by the standard deviation, we get a value of 6 points, right? So we get a net effect of reducing RADS by 6 points. Note, we also get a robust effect. It's a medium effect, but at 0.43, it's a pretty robust effect for psychology. Now, this is not trivial here, right? If we would have left our alpha at 0.001, we would have missed a true effect, right? Because there's no reason to not set that alpha at 0.05, right? We're not doing drug research on human beings here. We're worried about getting sued, right? We're doing psychology to see if, we're doing experiments in psychology to see if the effect of our experiment improved something or changed something in some way. And here it did. And this is important because this intervention produces an effect of 6 points. So it has the possibility of improving the lives of our participants here in this situation, right? A net improvement of 6 points on the RADS is nothing to sneeze about. And that's an effect we would have missed if we would have set our alpha too conservatively. So, think about this idea of statistical and practical significance and think about how our alpha can have an impact on the likelihood of rejecting or failing to reject a null. Particularly when it would cause us to miss an effect like that. So again, let's rewrite this up now under this new criteria here, right? We reject the null hypothesis, right? Our z is negative 1.66 with a p value of less than 0.05, and it would also be appropriate to report Cohen's d, right, which was 0.43, and we would want to italicize that. And now we're saying participants who experienced the intervention had significantly lower RAD scores than our population average. So that's very important. So our alpha has an impact on our likelihood of rejecting the null, but our effect size also matters too. What if we kept our alpha at 0.01 or 0.001? But we increased our sample size, right? I think before we had a sample size of 15, if I recall correctly off the top of my head. I don't know. Let's see if I can go back and find that really quickly without. It looks like I got to go all the way back, but I want to know, where was it? You're back here somewhere, are you? There's the known program. Yeah, our sample size was 15. There it is right there. Our sample size is 15. Okay, great. For this example, right, for this thought experiment, if you will, to explore how sample size can influence our likelihood of rejecting the null, let's bump our sample size up to 60. And we don't need to go through the steps of hypothesis testing again. We're just going to run our test statistic. And we're going to keep our decision criteria at 0.001. So that means our test statistic has to be less than negative 3.10, right? That's the critical value that we had looked up in our table when we first ran this analysis. But the only difference is we're going to boost our sample size from 15 to 60. So if we compute the standard error of the mean, right, a standard deviation of 14 divided by a square root of 60, it's going to give us a standard error of the mean of 1.807. If we then compute the test statistic, right, so we take the sample mean minus the population mean, divide that by the standard error of the mean, we get a test statistic of negative 3.32. And if we plot that, right, if we plot that into our distribution that we plotted earlier, right? Negative 3.32 falls in our critical region, right? Falls beyond this value of negative 3.10. So we reject the null, right? So increasing our sample size can also increase the likelihood that we would reject the null hypothesis. So here it is. Increasing sample size increases the likelihood of rejecting the null, and increasing our alpha increases the likelihood of rejecting our null. And be careful here. Remember, our conventional alpha is 0.05. You might say, well, why don't we just increase our alpha to 0.20, right? Well, that means we're taking on a 20% risk of making an error, right? So why 0.05? Well, over the century and a half of doing psychological research and using statistics, really since the early 1900s of using statistics and research, we've come to this agreement, if you will, in the community that 0.05 is an acceptable alpha, right? It's not so big that we're constantly seeing effects when there are none, but it's not so small that we're also constantly missing real effects, right? So over 100 and some odd years, we've came to this conclusion that an alpha of 0.05 is the sweet spot, if you will, right? So we don't make it any more than that, and typically, unless we have a very good reason, we don't make it any less than that. All right, so here's the 6 steps of hypothesis testing, and here I've filled in a little bit more detail here, right? And I think that just generally speaking, this is a good slide to commit to memory, because we're going to be doing these 6 steps over and over and over again across a variety of different statistics that we'll learn over the remaining semester. Also, like I said, this may or may not be on an exam. I don't know. If it is, then you'd be in pretty good shape. And if it isn't, well, you've learned something that you very much need to know anyway when doing testing in psychology. All right. Switch gears to a little bit of theory here. Hopefully this is an idea that's not too difficult to wrap your head around, but it's an important idea, and it has to do with alpha, and it has to do with sample size and all these little ingredients that go into making a good experiment, right? We always hope in science that our statistical tests are going to lead us to making the correct decision, right? So let's say in reality, there's no difference between our sample mean and the hypothetical population mean, and we run a statistical test, and our results confirm that. I mean, that's unfortunate in a sense because we don't want to report null results. But if it's true, then we're glad, right? Because we want our statistical test to reflect the reality, right? There's another alternative there, and that is reality that there is a difference between our sample mean and our hypothetical population mean. And we run a statistical test, and indeed the results of that test confirm that idea. So that's good too, right? That's even better because we were hoping there was a difference, and indeed our statistics say there is a difference, and it reflects reality. Like in reality, there really is a difference. So, one of these two situations makes us more happier than the other, but they're both good in the sense that our test reflects reality. That's sort of the key idea here when we think about this concept of type 1 and type 2 errors, right? So why do I bring this up? Well, there could be times where sometimes the results of our test don't reflect reality, right? And these are type 1 or type 2 errors, right? So a type 1 error is what we call a false positive error. The null hypothesis is correct, but the results of our statistical test cause us to reject it in error. And that's the key thing here, the results of our statistical test. So we ran a test, and it caused us to reject the null hypothesis in error. We didn't lie, there wasn't any deception. We ran a test, and the test caused us to make the wrong decision. So in other words, the statistical test says there's a difference between the sample mean and the hypothetical population mean, but in reality, right, there isn't one. So let's use our baby crawling data as an example here, right? So the reality is that my vitamin has no effect on the age that infants learn to crawl. Yet the results of my statistical test, right, when I ran my statistical test, it actually led me to conclude that it did have an effect. So I've made a type 1 error here. I've committed a false positive error. So why does a type 1 error occur, right? How is it that we make a type 1 error? Well, chance, bad luck, right? We just happen to select a sample that's in the extreme, right? Remember, when we generate a sample mean from a sample, there's a good chance that our sample mean is going to approximate the population mean, right? I mean, we talked about that in chapter 7. But imagine, right, I run a study, I do everything right. I randomly sample, I randomly assign people to groups, I control for extraneous variables, I design an experiment that's good, it's a well-designed experiment, it's measuring what I'm trying to measure, right? So I do everything right. However, strictly by chance, I end up sampling a sample mean that's unusual or extreme. So in other words, just by dumb luck, several people from my sample, most people from my sample maybe, end up coming from the tail of my distribution completely by chance. And this could happen. It's rare, but it could happen. And if this happens, right, then we reject the null hypothesis, right? And the results of our statistical test show a significant result, then we reject the null hypothesis and error. We didn't do anything wrong. It was just bad luck. So what's one way you can make a type 1 error, right? You can say you found a difference between means, but there really wasn't one. How do you protect against this? Well, you can't do anything about it in the moment, right? But replicating results certainly helps us protect against type 1 error, right? Because if we pulled another sample from that population, obviously it's more likely that sample mean would better approximate the population mean, and then in case we would have made the correct decision, which is failing to reject the null. Another way that we can make a type 1 error is that our alpha is too high, right? Our alpha is too high. Again, typically we set it around 0.05, and we're willing to accept that as a level of risk that we're willing to assume. But a lower alpha means that there's a lower chance for committing a type 1 error. So you could reduce it from 0.05 to 0.01 or 0.001, but there's a trade-off, and it's a trade-off we typically don't like, which is why we leave it at 0.05, because too low of an alpha level, and we risk making what we call a type 2 error, right? So this is where the null hypothesis is incorrect, right? So our alternative hypothesis is correct, but the results of our statistical test cause us to fail to reject the null. So in other words, the stats say there's no difference between the sample mean and the hypothetical population mean, but in reality, there actually is a difference. So let's think about it in terms of the baby crawling data again, right? So let's say my vitamin had an impact on the age in which babies learn to crawl. Like in the real world, it really worked, right? But the statistical test I ran led me to believe that there was no effect, right? So I missed it, right? So I've made a type 2 error. I've committed a false negative. How do we make a type 2 error? Well, there's a couple things I'm gonna talk about power, right? But the most common thing, and this relates to power, is that our experiment was underpowered, right? And one of the big things is that our sample size was likely too small, right? It's usually because we didn't run enough participants in order to determine that there was an effect. So power, right? This is the probability that our test will correctly reject the false null hypothesis, right? This is our ability to detect an effect that actually does exist in the real world. So put even more simply, power is the probability that there's a real difference between means and our test will detect it, right? We want to be able to say that there is a significant difference, and we want to be correct in saying that there's a significant difference, right? So if my treatment has an effect, right? If the population that my sample comes from really is different from sort of the known population, will I be able to detect this effect? And there are several factors that affect power. There are several factors that affect our ability to correctly detect a true effect. One is effect size. A larger effect size is typically associated with higher power, right? And this should hopefully make intuitive sense, right? Bigger effects are easier to detect. So when you're looking for a bigger effect, then by default, your experiment has more power. So imagine a scenario where you're using a telescope to look at the night sky, right? Like, so imagine two students, they take a telescope out and they try to detect the differences between stars, right? In terms of magnitude of luminosity. And one student is trying to detect whether star A and star B differ. And in reality, they do, right? If we were to hypothesis test that, we'd reject the null. But the difference in luminosity between star A and star B is really, really small. It's there, but it's really, really small. The other student is trying to detect whether star C and star D differ. And again, the reality is that they do. And the size of the difference is huge, right? It's much bigger. Well, in this scenario, who has more power in their observation? The first student or the second student? Well, it would be the second student, right? Because that second student, the difference between star C and star D has a bigger magnitude than the difference between star A and star B, right? So the larger the differences between means, it makes it easier to determine if there's a difference when there really is. So a larger effect size is associated with an increase in power for your experiment. Alpha level also matters. As alpha level decreases, then your power decreases, right? So it hurts you. When we decrease our alpha, we're shrinking the size of our critical region. And that means the sample mean has to be even more extreme before it falls in the critical region. Now, we want to avoid type 1 errors, so we keep our alpha pretty low, right, at 0.05. But the smaller it is, the harder it is for our hypothesis test to classify samples that do, in fact, differ from the population as unlikely. We saw an excellent example of this in our RADS example, right? When we had set the alpha at 0.001 and ran our statistical test, we failed to reject the null. But note that when we changed that to a more conventional level, right, when we increased our alpha to 0.005, we were able to reject the null hypothesis. And we noted a very powerful effect. So increasing our alpha increases the size of our power. But again, we don't increase it any more than 0.005. And then the last thing that affects power is sample size, right? As our sample size increases, our sample mean is going to become a more accurate estimation of the population mean. So as sample size increases, power increases. And remember, the law of large numbers, right? So we saw this when we left our alpha 0.001 for the RADS test, but increased our sample size from 15 to 60, right? When we increased our sample size, we increased the power of our experiment, and we were able to correctly reject the null hypothesis. But here's just a little question for you to sort of think about in your head. If increasing our sample size reduces things like standard error, it brings our sample mean closer to our population mean, why don't we just continue to collect data until we get our result, right? Until we reject the null, p is less than 0.05. So let me give you this scenario. Let's say we've ran 40 people in an experiment, and we compute the statistical test, and p is greater than 0.05. There are ways you can use the computer to compute your exact p-value. So let's say we get p equals 0.08, right? So we failed to reject the null. Well, let's say we throw a little bit more data at it, because think about the law of large numbers. As I increase my sample size, my sample mean starts to become a better approximation of my population mean. My overall variability decreases. All of these things increase the likelihood of rejecting the null hypothesis. So let's say I go from 40, and out of 40 to, say, I collect 10 more participants of data, right? And now I compute my p-value, and it's p equals 0.03, right? So that's less than 0.05, right? I reject the null hypothesis. So why not, for every experiment, why don't I just keep collecting data until I get the result I want? Well, the problem is that's cheating. We have a term for that. We call that p-hacking. And it is deceptive, right? Prior to running an experiment, you should engage in a practice called power analysis or Monte Carlo simulations. Now, these are all statistical tests that are beyond the purview of an introductory statistics class. It's something that you can learn if you were interested in a career in science, for example, went to graduate school. That's where you learn it. But there are two sorts of statistical tests that allow us to compute exactly what our sample size should be in order to correctly reject a false null, right? So in other words, if there's a real difference, this is exactly the number of people we would need to run in our experiment in order to detect that there was a difference. And you should run no more and no less than that. If you run less than that, you're shooting yourself in the foot, right? Because again, think about our example with RADS when we set our criteria at 0.001 and only collected data on 15 people. We failed to reject the null, but when we collected an appropriate sample size, well, then we successfully rejected the null, right? So you want to run the exact number of people that your power analysis or Monte Carlo simulation suggests that you should. No more, no less. If you run any more, then you're cheating, right? You're committing p-hacking. And this is why a lot of journals today are insisting that you publish the results of your power analysis or your Monte Carlo simulation, and that indeed the sample size that you present in your data accurately reflects the sample size that your simulation or your power analysis should reflect. Because this makes it easier. It's more transparent, right? It's a way of doing it with integrity. So you know, and everybody knows that you're not p-hacking. So, but again, running those sort of tests is beyond the purview of this class. If you got involved in some research as an undergraduate volunteer, whoever's running the lab or the graduate student in the lab should have already computed that prior to running the experiment. Okay, so let's go through two more examples, right? This is, we're going to go through all 6 steps of hypothesis testing, and you should feel quite comfortable doing this, right? So here's the scenario, right? So a therapist has developed a new technique that she believes will reduce the amount of time that people with schizophrenia spend in hospital care. The mean duration of all hospital stays is 85 weeks, with a standard deviation of 15 weeks. 25 people with schizophrenia are randomly sampled from a nearby mental health hospital. The results of the experiment show that the patients treated by the therapist stay a mean duration of 79 weeks with a standard deviation of 10. The alpha is 0.05. All right, you can do this. I want you to go through all 6 steps of hypothesis testing and pause the video. And when you come back, I will guide you through and you can compare your work to mine. So step 1, state the null and the alternative hypotheses. Is this a one or a two-tailed test? All right, so you should have established that this is a one-tailed test, right? Because she's making a prediction that she will reduce the duration of stay and hospitalization for people with schizophrenia, right? And again, when that's the case, you want to do the alternative hypothesis first. Reduce implies less than, right? Less than. So the alternative hypothesis, H subscript 1 colon, the mean duration for our samples should be less than 85 weeks, which is the population mean. And be careful. Let me go back to the slide. You'll note here I'm talking about the population data. 85 weeks is the mean, 15 weeks is the standard deviation. And note down here I'm talking about the sample data, right? So don't confuse sample data with population data, right? So again, the mean duration should be less than 85 weeks. The null suggests the mean duration should be greater than or equal to 85 weeks. So now we want to determine the decision criteria, right? So what's our alpha? Is it a one or two-tailed test? And where should our critical regions go? Well, again, our alpha was set at 0.05. This is a one-tailed test. And based on the alternative hypothesis, which was less than, right? Less than, the entirety of our alpha should go in the left part of our distribution, so in the left tail. So again, we want to find a point in the distribution that separates the bottom 5% from the top 95%. We're looking for 0.05 in the tail, finding the z-score associated with that. So we've done this a couple of times now. The closest value without going over is 0.0495. That gives us a z-score of 1.65 for our critical value, but in reality, we really mean a negative 1.65. So when we compute the z-score, if it falls in this region, we would reject the null, because it's falling within the critical region. But if it falls outside of the critical region, we would fail to reject the null. And now we want to compute the test statistic. Here's our data, right? So again, be careful here. I've given you the sample standard deviation, but that doesn't matter for our equation, right? We're only interested in things like population mean, population standard deviation, sample mean, and the sample size, right? The first thing we want to do is compute our standard error of the mean, right? So we're going to take that population standard deviation. Again, the population standard deviation, not the sample standard deviation. So don't get fooled. Sometimes you'll read these scenarios and there will be little lures in there, right? Don't get fooled by these little lures. Always remember what goes into what, right? The standard error of the mean requires the population standard deviation, not the sample standard deviation. So anyway, if you compute that out, you get a standard error of the mean of 3. And if you finish computing the z statistic, right, 79 minus 85 divided by 3 should give you a z statistic of negative 2.00. Now you have to make a decision, right? Return to your normal curve that you plotted where your critical value is. Plot the results of your z statistic. Does it fall in the critical region? Indeed, our z statistic of negative 2.00 does fall into our critical region. So the correct decision is to reject the null. And now that we've rejected the null, we need to compute the effect size, right? Which is nothing more than our sample mean minus the population mean divided by the population standard deviation. So 79 minus 85 divided by 15 is going to give us a Cohen's d of negative 0.40. But remember, round to 2 decimal places and report that as an absolute value. So Cohen's d equals 0.40. In thinking about interpretation, again, that's a net effect of 6 weeks. It's a medium effect. So it's a pretty robust effect, right? It looks like the therapist's technique has dramatically reduced the effect of hospitalization for patients with schizophrenia. So now we need to write these results up in APA format. So we reject the null hypothesis. That's the first statement we should write down. Then we want to report our z-score that we computed. And then p less than whatever our alpha is, because we rejected the null. So that should be p less than 0.05. And Cohen's d, our effect size, equals 0.40. And then we want to say something about the difference between our sample mean and our population mean. So the average hospitalization stay was shorter for patients who were treated with a new technique. And here we report the mean and standard deviation for our sample, because that's what we're describing, compared to the population average. And there we report the population mean and the population standard deviation. So hopefully that went well for you. Let us try one last example. So again, I want you to run through the 6 steps of hypothesis testing. So here we have an example where an automotive engineer believes that her newly designed engine will be a great gas saver. A large number of tests on engines of the old design yielded a mean gasoline consumption of 27.5 miles per gallon with a standard deviation of 5.2. So we'll treat this as the population data. 16 new engines were tested. The mean gasoline consumption is 22.7 miles per gallon. The alpha is 0.05. So go ahead and pause the video, do the 6 steps to hypothesis testing, and then come back, unpause the video, and compare your work to mine. So state the null and the alternative. This is a one-tailed test, right? Because her prediction is that her new engines should reduce fuel consumption, right? So the mean miles per gallon for her engine should be less than what we're treating as the population data. So our alternative hypothesis should reflect that directional prediction, right? So the mean miles per gallon of the sample engines should be less than what we're using as the population, which is 27.5 gallons. Our null hypothesis should simply be the opposite of that with an equal sign. So our mean sample should be less than or equal to, greater than or equal to our population data of 27.5 gallons. This is an alpha of 0.05, a one-tailed test. Again, the prediction is less than, so all of our alpha, all 0.05 of it should go in the left side of our distribution, so in the left tail. So again, we draw a line through the distribution separating the bottom 5% from the top 95%. We've become grizzled veterans at finding these critical regions, right? So 0.05 all in one tail. Well, that value that's closest to 0.05 without going over is 0.0495. So that gives us a Z critical value of 1.65, but really negative 1.65. So again, anything less than that, when we compute our statistic, we're going to reject the null. Anything greater than that, we're going to fail to reject. So again, we're going to compute our test statistic. Here's our sample data. Here's our population data. First thing we should do is compute the standard error of the mean. So we're going to take the sample standard deviation divided by the square root of our sample size. And that's going to give us a standard error of the mean of 1.3. When we subtract our sample, or rather when we subtract the mean, population mean from our sample mean, and divide that by the standard error of the mean, we get a computed sample statistic, a Z statistic of negative 3.69. When we plot that into our normal curve, right, where we've went ahead and found where our critical region would be, we see that indeed it falls in the critical region, and we should reject the null hypothesis. Because we rejected the null, we want to compute an effect size, right? So again, here's the pertinent data and the parameters for our test statistic. When we compute our Cohen's d, we get a value of negative 0.923. But again, we want to round to 2 decimal places and report as an absolute value. So our actual effect size is 0.92. Very robust, her engines lead to a 4.8 mile per gallon improvement. And as you can see, it's quite a large effect, which is pretty uncommon to find an effect that large in psychology. But in this instance, with these sort of made-up data that we're using, we found quite a large effect. So now we need to write up these results in APA format, right? So we reject the null hypothesis. We report the result of our Z statistic, P being less than our alpha because we rejected the null, so P less than 0.05. Because we rejected the null, it's appropriate that we report our effect size, which was 0.92. And we want to state something about how our sample differs from our population. So the newly designed engines demonstrate improved fuel economy, there's the mean, compared to the older engines. And there's the population mean and population standard deviation. So again, hopefully that's what you got. If you didn't get that, compare your work to mine. And see where you went wrong. If you have any questions, let me know. Whew, we made it, right? So if you want some additional practice, help you get ready for the exam or just get more comfortable with these concepts, here's some questions from the back of the chapter. And that's it. So hopefully you're awesome at computing hypothesis testing for one sample Z statistics. After this, we're going to switch gears to what do we do if we don't know the population standard deviation, because that's going to be a situation that often occurs when we're doing statistics in psychology. So we'll learn how to compute a t-test, a one sample t-test, when we do not know the population standard deviation. But we'll worry about that for the next go around. Okay, so good luck.